complex number z has modulus 5 and 1/16 and argument 4 pi over 9. Find in polar form the four complex fourth roots of z. Let's first look at the argument of z. The argument is measured anti-clockwise from the positive real axis, because this is positive, this angle. It's plus 4 pi over 9. We could get a rough idea of what this angle is by looking at it in degrees. Remember, pi radians is 180 degrees, so we have 4 times 180, and then we divide by 9. So in degrees, our angle is 80 degrees. So the complex number must be in this quadrant here. The modulus, or the distance of the complex number to the origin, is 5 and 1/16. So we have a complex number somewhere in this quadrant. So this is 5 and 1/16, and the angle, which is normally called theta, is 4 pi over 9. All complex numbers can be written in this form here. This is called the polar form of a complex number. R is the modulus of the complex number. So in this case, R is equal to 5 and 1/16. Theta is the argument. So theta is 4 pi over 9. Now, since we will be getting roots of this complex number, we should write down what's called the general polar form. That's got by adding integer multiples of 360 degrees onto theta, or integer multiples of 2 pi. 2 pi radians is 360 degrees. So we just replace theta with theta plus 360n, or 2 pi n, where n is an integer. It could be positive or negative whole number. So remember, pi radians is 180 degrees, so 2 pi radians is 360 degrees. So this angle here is 360 degrees. So this is the conversion for radians to degrees. So for this particular complex number, we plug 5 and 1/16 in for r. We plug 4 pi over 9 in for theta. Now I'm writing this angle in radians. You could convert it to degrees. We saw already that this is 80 degrees, but then we would have to write, instead of 2 pi radians, 360 degrees times n. So general polar form just involves adding on this term here, which is just a multiple of a full revolution. So for example, if n is 1, we just add 2 pi, we're just back to where we started. So it doesn't affect the value of the cos function by adding multiples of full revolutions onto our angle, because we just keep coming back to where we started, no matter what value n is. Provided n is an integer, of course. N must be an integer. That's very important. The same is true for the sine function. Sine function isn't affected by adding on integer multiples of full revolutions, 2 pi radians or 360 degrees. Now, what we want to do is get the four complex fourth roots of z. In other words, we want to calculate this thing here, the fourth root of z, which can be written as z to the power of 1/4. So basically we want to put all of this number to the power of 1/4. So we have a product here of 5 and 1/16 times all of this. So we put each part of the product to the power of 1/4. So we put 5 and 1/16 to the power of 1/4, and we put everything in here to the power of 1/4. Here is 5 and 1/16. We put it to the power of 1/4, which is 0.25. Get 1.5. Now this is true for all integers n. Now let's look at the part in brackets raised to a power. Now this is where we use de Moivre's theorem. De Moivre's theorem says that we can multiply this power, which is 1/4, by the argument of the cos and sine functions, or the angles. If we multiply a quarter by 4 pi over 9, we get 4 pi over 36. A quarter times 2 pi n is 2 pi n over 4, which is pi n over 2. So this is the general form for a fourth root of our complex number z. But we will get different answers depending what n is. So let's look at n equals 0. N must be an integer. So we start with n equals 0. Plug it in here, and one value for our root is going to be 1.5 into the cos of 4 pi over 36. Actually, I can simplify 4 pi over 36 to pi over 9. This part would be 0 if I put 0 in for n. So that is one root of z, one of the fourth roots of z. Of course, n can be 1. So we just plug 1 in for n here. So another solution is 1.5 into cos of, well, this is actually pi over 9. Pi over 9 plus, if we put 1 in here, we get pi over 2 times 1. So we have pi over 9 plus pi over 2. You could work that out in your calculator by putting in 1/9 and adding on a half. So 1/9 plus a half is actually 11 over 18. So we continue on like this. Now we choose the next integer value of n, which is 2. We could have chosen negative values for n, but the negative values will just give us, will actually work out to give us the same results. Well, not exactly the same, but the same results maybe in reverse order. For example, n equals -1, I think will give us the same result as n equals +3. So you don't have to worry about negative values for n. Just start with 0 and work up. Normally, for the fourth root, there will be 4 roots. So we'll have to go as far as n equals 3 in this case. Now, n equals 2. What will that give us? Well, we've pi over 9 plus pi times 2 over 2. That's just pi over 9 plus pi. That's like 1/9 pi plus 9/9 pi. That's 10/9 pi. And finally, we have n equals 3. So we'll have 3 distinct roots. If we plug 3 in here, we'll have 3 pi over 2 plus 1 pi over 9. Well, we could write 1/9 as 2/18 and 3/2 as 27/18. So 27/18 plus 2/18 is 29/18. These 4 roots are actually distinct. You see that these angles are different, and the cos of these angles will be different. So will the sines. If we were to go to say n equals 4, we would just get back the root that we got for n equals 0. If we plug 4 in for n, we get 4 divided by 2, which is 2. So we'd have 2 pi. We are adding 2 pi onto pi over 9. Well, the cos of 2 pi added onto an angle doesn't change the value of the cos function. The cos of pi over 9 plus 2 pi is the same as the cos of pi over 9, because 2 pi is a full revolution. It's 360 degrees. So if we plug in 4 here, this would just we won't change the value to cos or the sine functions. So we're just getting the same result we would get if we plugged in n equals 0. So we're just going back around. And if we were to plug in n equals 5, we would get the same result as if we plugged in n equals 1. as then we're just adding another pi over 2 onto the previous, just like we did here when we went from 0 to 1. We added on an extra pi over 2. So we will just cycle through these solutions as we increase values of n. N equals 6 will give us the same result as n equals 2, and so on. So because we're getting the fourth root, there is a theorem called the fundamental theorem of algebra that tells us that there are at most 4 distinct roots. If you want to, you can go and evaluate this here. 1.5 times the cos of pi over 9 is 1.41 to decimal places. 1.5 times the sine of pi over 9 is 0.51 to 2 decimal places. So, you can do this, but normally you can just leave them like this. Leave the complex numbers in polar form. Z is marked on the argand diagram below. Remember, Z was the complex number with modulus 5 and 1/16, so the distance of Z to the origin is 5 and 1/16, and its argument was 4 pi over 9, or 80 degrees. Now we got the fourth roots of Z, so that involved getting the fourth root of 5 and 1/16, which is 1.5. So these complex numbers have the same modulus. It's 1.5. They all have this. The distance of them from the origin is 1.5. We want to show them on this diagram. Let's look at this first complex number here. What is pi over 9? Well, just to get a rough idea of what it looks like, we can convert it to degrees. Pi is 180 degrees. 180 divided by 9 is 20 degrees. So the first complex number makes an angle of 20 degrees measured anti-clockwise from the positive real axis. So we measure 20 degrees from the positive real axis, and we make the modulus of the complex number equal to 1.5. So one might look roughly here. So the distance of this complex number to the origin is 1.5, and this angle in here is 80 degrees, or sorry, 20 degrees. Pi over 9 radians are 20 degrees. We could call this complex number omega 0. Now let's look at the next complex number, which we could call omega 1. Well, the only difference between omega 1 and omega 0 is that we're adding a certain amount onto the angle of omega 0. If you think back to how we found omega 1, we plugged in n equals 1, and we were adding basically pi over 9 onto this angle here. Excuse me, we were actually adding pi over 2 onto this angle. So we could get omega 1 from omega 0 by rotating this complex number actually anti-clockwise about the origin. Anti-clockwise through an angle of pi over 2, which is 90 degrees. So to go from pi over 9 to 11 pi over 18, we just add on pi over 2. As a matter of fact, that's what we do all the way through. We just keep adding on pi over 2, which is 90 degrees. That actually has the effect of rotating anti-clockwise through 90 degrees. So here I'm calling the other complex numbers omega 2 and omega 3. So we just rotate anti-clockwise by pi over 2 radians, or 90 degrees, and we get omega 1, which is 1.5 units from the origin. Then rotate by another pi over 2 anti-clockwise to get omega 2, which is also 1.5 units from the origin. The moduli of all these complex numbers are 1.5. As a matter of fact, these 4 complex numbers form the corner of a square. Form the corners of a square. So if we have the 4th roots of a complex number, a square is formed. If we had, say, the 5th roots of a complex number, then we would have a pentagon. we always get a regular shape. Here is a better picture. I rushed through the last diagram. Omega 1 is more like up here. If we rotate omega 0 through 90 degrees, it'll look like it's up here somewhere rather than where I had it. Of course, you could just work all of these out in your calculator and try to plot them reasonably accurately, but it's much easier to take advantage of the fact that these complex numbers are equally spaced and they all have the same distance from the origin. It makes it easier to get a rough sketch.